Okay, we're on live now.
Great,
Okay.
thank you. Now, if you have ever studied regular continued fractions, alpha continued fractions, Lorentz series, generalized Lorentz series, beta expansions, or in short, any enumeration series system for real numbers, much sooner than later, you end up studying Dr. Karma Dajani's work. Professor Dajani obtained her PhD in 1989 in Washington University in the United States. Her broad research includes number theory, dynamical systems, and ergodic theory. Moreover, and this is just a personal opinion, along with Cor Krijkamp, Professor Dajani wrote one of the best introductions to the interaction between number theory and ergodic theory, and I have even used it more than once in my own research. So without further ado, please welcome Karma Dajani with her talk titled Dynamical Behavior of Alternate Base Expansions.
Thank you very much, and thank you for this very nice introduction. I'm really overwhelmed with it. Okay, so my talk is joint work with Emily Charlier and Celia Cisternino from Liège in Belgium. And what I want to talk about is actually a generalization of beta expansions. So let me start. No, he doesn't want to click. Okay, so the expansions that we are looking at, instead of looking at one base as in the regular beta expansions, we're going to consider a sequence of bases. And just to keep the notation straight, that our n is going to start from 0, but of course this is no problem. So what I want to do is I want to start with a sequence of bases, beta n, and I call the sequence with bold beta, and I'm going to assume that not only they are greater than 1, but the product of the beta n's is plus infinity. This is just a technical conditions to make sure that all the expansions that we'll be looking at are actually convergent. All the series we're looking at are convergent. And we're going to call a beta representation, where beta now is bold and it's the given sequence, is a sequence of digits, AI, in the natural numbers, such that X can be written as you can see here. And you can see now that the base is not fixed anymore. The first base is beta 0, and then the next step I'll use beta 1, and then beta 2, etc. And the AIs, again, are digit sets, and the variation of the AIs depend on the base I'm going to be using at that particular step. So this will become clear in a second. So the expansions look like what I have at the bottom of the line. So in the regular case, when all the betas are the same, the product of the beta i's will be really beta to the I. So you'll get the classical representation. One way to generate them, there are actually uncountably many such representations. And one way to generate them is to use successively the normal beta transformation, or beta I if you are at the I stage. So it's just beta ix modulo 1. So the usual transformation, but at every step I'm using another transformation. And if I use these transformations, then the expansion that I get is what we call greedy, in the sense it's the largest in some lexicographical ordering, which is not the normal one because I'm changing my basis all the time, but we can make sense out of what we mean by the largest, and the expansion you get is the largest. So, but I'm going to concentrate on a special sequence of bases, which are periodic, and that's why we're calling them alternate base. So, so every p steps, I'll restart my base again. So my sequence beta is actually a periodic sequence of period beta, p, sorry, and just to ease the notation, instead of writing the whole periodic sequence, we simply denote it by beta 0 up to beta p minus 1. And when we write beta n, we always mean beta n modulo p. Okay, so I'm looking at a special counter base where the base itself is a periodic sequence. Now, these have been studied actually for a while, but recently it has acquired a lot of attention. And two of my co-authors were interested in it before I joined. They were really interested in the symbolic parts of it. And they've proved a lot of nice result, actually lots of generalizations of the classical case. What I mentioned before is that this beta is the largest in the lexicographical ordering. And another nice result is that the beta expansion of 1 cannot be purely periodic, that the greedy digits that I get are increasing in the base. And you can make sense of what we call quasi-greedy representations. These are the largest infinite expansions that you get. And there is also a generalization of Perry's theorem, which characterizing these expansion using the lexicographical the expansion of 1 and the lexicographical ordering. Also characterizations of the beta shift, when is it sophic and when is it a shift of finite type. And yeah, so I'm not going to be talking about these because these are done by other people, but just to tell you that lots of the old results have been generalized to this setup as well. Okay, my aim today is threefold, if I have the time for it. First, I will start by defining a dynamical system that generates these expansions, actually the greedy expansions. And then once we do that and study their dynamical behavior, I'm going to switch to the opposite side of the spectrum, which is the lazy expansion. And these are, in a sense, the smallest in the lexicographical ordering. And then the last part is because we are using an alternate base, that is, our base sequence is periodic. This means every time I group P terms together and rewrite the expansion, I will end up with expansion with a base which is the product of the betas, but it looks like the classical greedy expansion, except the digit set is no more integers, but it lies in a Q of the product of the beta i's. So, and I would like to characterize when do we get, when are these greedy when I block them together. But of course, now it's being a bit vague. When I come to the third one, it will become clear what I mean by that. So let me go to the first item, which is quantifying what we mean by a greedy expansion in this system. Okay, so I have my periodic beta, and when I have double brackets, 0 to p minus 1 double bracket, this is just a shorthand of the integer interval 0, 1 up to p minus 1. So my beta transformation is going to be living on a bigger space. The first coordinate is going to tell me which transformation to apply. And that's on the second coordinate, the 0, 1, are the points that I'm trying to expand. And the transformation is really as simple as you can think about. So if I pick a point ix, so then the image will be I plus 1. So I go in a sense my space are p copies of the unit interval, and if I'm on the ith level or ith floor, then my next step I will move to the ith plus 1 floor, and I do that by applying the map t beta I. So it's just the first coordinate just tell me which floor I am in and which transformation I need to apply. So if you start on the 0th floor, so your point is 0x, and you apply your transformation n times, then in the first coordinate, you simply get n modulo p. And in the second coordinate, you see compositions of these various t beta i's. And starting with, because I started with the 0th floor, then I will start with the map t beta 0 and then t beta 1, etc. And then once I reach t beta p minus 1, then I restart again with beta 0. And the beta expansion in this new sense will be read from the second coordinate. So these compositions are going to tell me what my digits is going to be. And it's going to look a little bit familiar, but of course generalized a little bit. So the nth digit, I get it by looking at the nth orbit, that is after applying t beta 0 up to t beta n minus 1, I multiply this by beta n, and I take the floor of this. And this will tell me what my digit is. And you see that at the nth level, my digit set is actually changing. So on the 0th floor, I'm allowed to use 0, 1 up to floor of beta 0. On the first floor, I'm allowed to use 0, 1 up to floor beta 1, etc. And we write it in this weird way with a ceiling -1, just because we want to include the integer case as well. And yeah, in this way, we are taking both options into consideration. Okay, so this is just a visualization of my space. As you see, it's n copies of the unit interval, and the levels are designated by the first coordinate that I have here. And if you are on the 0th floor and you apply your map p times, then you return to the 0th floor. So you make a whole cycle after p iterations. And the same thing, if you start on the ith floor and you apply the map p times, you return to the ith floor. And what you're seeing on the right side maybe looks a little bit weird, but remember, when I say beta I minus p, I'm taking this modulo p. So I'm actually starting with beta I, in fact. So I go, if I'm, let's say, on the first floor, I start with t beta 1 and then t beta 2 until I hit the ceiling. And then I go back to the base and I start again. Okay. So I'm just explaining again what I just said, that the p-fold composition, if I start with the ith map, it's just what I said. You start with beta I until you hit the top, and then you go to the bottom and start ascending again. And all these maps, if I look at p-fold compositions, then I get piecewise linear maps of constant slope, which is the product of the betas. And all the lines are starting from 0. And this is really an ideal situation that has been studied all through, actually through from the 70s. And these maps are very well understood. For example, by now, a folklore theorem of Lasota and York tells you that if you have piecewise linear maps that start from the origin, then there is an absolutely continuous invariant measure. In fact, it's equivalent to Lebesgue measure. And it has a bounded density from below and from above, which is a very desirable thing. And all the maps are exact, which means they have trivial tails. And in fact, what's so important about exactness is that it gives you, this implies all the attractive dynamical systems that we like, basically that they are all exact and ergodic. And the entropy is just log of the slope of the lines, which is the product of the betas. So the p-fold compositions are really well understood. And the measure that we get, which by doing the p-fold composition starting from the I floor, which I denoted it by mu I. So this will be associated with the ith floor, and these will form really the components of the invariant measure for the big system, for the script t beta. Okay, so just to formalize things correctly, of course, if you talk about measures, you need sigma algebras. And because our space is just a disjoint union of p floors, so I just take the union of the Borel sigma algebras on each one of the floors. So it's just a natural sigma algebra to consider. And if I have a set in this sigma algebra, which is, let's say, a union of sets on each floor, union of I cross pi, then the measure of this set is simply the average value of the measure of the, so bi really lives on the ith floor. So I look at mu I of bi for each I, and then I take the average over the p sets, p measures that I get. And in particular, if my set A just lives on the ith floor, so it's of the form I cross pi, then I simply get the mu I that I discussed before, which is the invariant measures for the p-fold composition starting with beta I. It will be divided by p, just because I'm taking the average over p. All the other ones are 0, so I end up with mu I, pi over p. Okay, and of course, I want to show that this measure that I just defined is invariant for the big transformation. And this follows from a very easy observation. Namely, if I take a set B and I see it, it's in 0, 1, but I see it on the ith floor, and I measure it via the measure mu I, I get the same answer if I were to pull it down to the i-1 floor. Of course, I pull it down via the map t beta i-1, and so I am on the i-1 floor, and then I use the measure designated to that floor, which is mu i-1. I get exactly the same answer. And the reason is, if you look at the right, I said that mu I is invariant for the p-fold composition starting from t beta I. To show this equality, all you need to show is that the measure that I defined on the right-hand side is also invariant for the p-fold composition, which is very easily seen to be true. And a nice result from ergodic theory, which is really a consequence of the ergodic theorem, that says two ergodic measures for the same transformation are either mutually singular or are exactly the same. And because both of these measures are equivalent to Lebesgue, you see that indeed these two measures are the same. And once we have this equality here, then it's an easy task to show that the big transformation script t beta is t invariant, simply because if I take a set which is a union of sets on each floor and I look at its inverse image, then what I'm doing is just taking the inverse image of each floor with the appropriate map. And from what we discussed in the lemma, this tells you that, this will have the same measure as the one that you started with. So it's really an easy task once you have the lemma. Okay, so that's the first thing. When we want to do ergodic theory, basically we want two essential things. The first one is to find an invariant measure. And if it is equivalent to Lebesgue, that we really like, because this is a physical measure that we see. And so we have the first ingredient, which is a t invariant measure equivalent to Lebesgue. And the second ingredient that we like is to have that the map is ergodic. And that's also the case. I usually don't like to put proofs in talks, but this is such a simple exercise. You can give it to your students. So the ergodicity really follows also quite easily, because if I take a set A, which is a union of sets on each floor, and I assume that it is invariant with respect to my big transformation, and just recall that when I write Bn, I mean Bn modulo P. So if I look at what inverse image of A is, and A is this union, so I look at the inverse image of each term in this union, then I see what I have here. So this means I move things to the i-1 floor via the map t beta i-1. And because A is invariant, this tells me that my right side here should equal to the i-1th component of my set A. So this gives me that these two sets are the same. And I can apply this over and over again. And I see that any composition I take, if I start with Bi and I take the inverse image of, say, n compositions, then I end up with a set Bi minus n. Of course, it's read modulo P. So in particular, if I take n is P, which means I make a complete cycle, then I see that the Bi that I start with will be really invariant with respect to the n-fold composition. And these we have seen are ergodic. So this tells me that each floor has measure 0 or 1, but with respect to the measure mu I designated to the ith floor. So this means the components of my set A, each component has measure 0 or 1, but I want A to have measure 0 or 1. So this means because with the measure of the big system is the average of the measures of these component ones. So to show that it has measure 0 or 1, we need to show that each Bi, either all of them have measure 0 at the same time, or all of them have measure 1 at the same time. But because these measures are absolutely or equivalent to Lebesgue, this is equivalent to saying all the Lebesgue measures of these sets are 0, or all of them are 1. And Lebesgue measure is non-singular, or the transformation T beta I is non-singular with respect to lambda. And beta I plus 1 is related to beta I via this map. So this indeed tells me that if BI is 0, has measure 0, so does BI plus 1, etc. So all these sets must have measure 0 simultaneously or measure 1 simultaneously, which gives me that A has measure 0 or 1, and this proves ergodicity. Okay, and this measure, mu beta of the big system, is also equivalent to Lebesgue, but Lebesgue, in the sense I have n copies of my unit interval. So when I say Lebesgue measure on my tower, I mean the average value of my Lebesgue measure. And it's very easy to see that it is equivalent to Lebesgue. And in fact, you can, here I wrote the density still in an abstract way, but you can really find the explicit density of the invariant measure, which basically will be sum of indicator functions, as in the case of the classical beta expansion. So we understand this map very well, and we understand its invariant measure. And the next thing that one wonders is that each component, each floor, when I look at the p-fold composition corresponding to that floor, I get an exact transformation. So usually you think that it should be inherited by the big system, but it is not. And this is simply because an exact system has the property that all the pth power or pth iterate must be ergodic. And in this case, we do not have, because if you start with the base and you do p times, then you return to the base. So you have an invariant set, which is not trivial. So my big map is certainly not exact. It's just ergodic. Okay, so the next thing that one wonders about is the entropy. Can one calculate the entropy of this system? And the answer is yes, because we can understand this system via the induced system. So let me be more exact. So I have this big system, which is the script T beta. And what I want to do is I want to just induce on the ith floor, which means I just want to observe my system when it hits, starting on the ith floor. I want to put a blindfold on my face. And once I hit the ith floor again, I will look again. So in other words, all what it is because of this nice cyclic structure, the induced transformation on the ith floor is simply the pth iterate of the map if I start on the ith floor. And once we have the induced transformation, we can talk about the corresponding induced measure, which is simply the original measure, and then you divide by the measure of the set you are inducing, but which is the ith floor, and the measure of the ith floor is 1 over p. So when you divide by 1 over p, you end up that the induced measure is just p times the mu beta of this set on the ith floor, and this is really the mu I that we talked about, which is the invariant measure for the p-fold composition. So the induced measure is just mu I, and this is really not surprising. But just to make things more rigorous, I'm going to, because now we are looking at floors, so all I want to say is now I can, in a trivial way, I can do the following. I'm going to define a map delta I from the unit interval to the ith floor by simply attaching to an x I in the first coordinate to tell you I want to see x now on the ith floor. And there is a trivial isomorphism between the induced transformation on the ith floor, that's here, and the p-fold composition on the unit interval. So which means that all the nice properties that I talked about for the p-fold composition can be inherited by the induced transformation. So as a corollary of this, because this map, the p-fold composition, as I mentioned before, has entropy log of the slope, and the slope is just the product of the betas, then you see that the induced transformation has the same entropy, which is log of the product of the betas, which is of course the sum of log beta i's. So that's the entropy of the induced transformation on the ith floor, and this is true for any I. Maybe I should have used a different index on the right side, but that doesn't matter. It's clear, I think. And from this, we can see once you have the entropy of the induced transformation, then you can deduce from it the entropy of the big system, which will be the average of the sum of log beta i's. And this follows immediately from a very classical result, I think in the 60s, but I'm not really sure of the date, due to Abramov's, that connects the entropy of the induced system to the entropy of the big system. So the entropy of the big system equals the entropy of the induced system, and then times the measure of the set you are inducing. So you end up with this result. So we also know the entropy of this system. You see the time, yeah. Okay, so far I've been talking about my tower had just copies of the unit interval, and I was able to talk about the greedy expansion. So to talk about other expansions, we actually need to extend our domain. So what I'm going to do, first I start with the 0th floor, and I'm going to extend it as long as I can, which means I'm going to look at the point x beta for which I get the largest expansion. That is, if I use the largest digit at every step. So at level C0, I should use floor or seeding -1 of beta 0. And then when I get mapped to the first floor, I should use ceiling beta 1 -1, etc. So if I use artificially the largest digit at every step, I end up with x beta. So this is the point with the largest beta expansion, starting on the 0th floor. And I can imitate this for every floor. But of course, on the ith floor, my composition is starting with beta I. So for each floor, I'm going to have to assign a new sequence, which is just the shift of the original one. So beta I, I'm sort of shifting my original sequence until I start with beta I, and then my cycle starts. And I do the same thing. So if I'm on the ith floor, I use the largest digit from that point on. I get to this point, x beta I, and it's exactly the largest point on the ith floor the point with the largest beta I representation that is living on the ith floor. And it's very easy to see that there is a relationship between the largest point on the ith floor and the largest point on the ith plus 1 floor. In fact, T beta I maps the largest point on the ith floor to the largest point on the ith plus 1 floor. So now we know how to extend our domain. So we can now look at a bigger space. So as you can see now, on the ith floor, I'm going, instead of just looking at 0, 1, I'm going to extend it to the interval 0x beta I, and I do this for each floor. And I look now at my new extended, but I still call it T beta map, that maps the ith floors to the ith plus 1 floor in the same way as the old one, if x is in 0, 1. And if x is in the extended region, I just use the last line, basically the biggest line, to map it to the next floor. This extension has the same invariant measure as the old one because this extension is artificial, which means you can quite easily prove that if you start in the extended part, so after 1, and you apply your dynamics, eventually you will hit the interval 0, 1, and you will never leave it. So all the properties that we studied with the restricted domain, with the domain 0, 1, still apply here because the extended part dynamically is not seen by the invariant measure. But this is important if we want to look at other algorithms. As I said, there are uncountably many. And so it's important to extend our domain in order to be able to do that. Okay, so here's a picture, and it looks very much similar to the one I did before. The only difference is that now my levels are no more equally, have equal lengths, but they can have different lengths. But other than that, it's the same idea. If you start on any floor and you do a cycle of length p, then you end up back in the same floor you started with. So this is an example with two, where my periodicity is 2. So I'm using 2 bases, 1 plus the square root of 13 over 2, and 5 plus square root of 13 over 6. So as you can see, the blue lines, they have domain 0 x beta, only up to this point here, x beta, but they get mapped to x beta 1, and the other way around. The black lines have domain x beta 1, and they get mapped to x beta. So these are, if you don't want to look at levels, but look only at the maps, these are the maps that we are applying. And we can define the lazy in a very similar way like we did for the classical case. Basically, you can define it inductively by saying, suppose I have the first n terms, then the nth plus 1 digit will be the smallest element of the appropriate digit set. So this means I have to use 0, 1 up to ceiling beta n minus 1 in such that when I put my digits from 0 up to n, and I put the largest possible tail, then I'm still I'm above x. So this basically tells you that if I shrink my tail, I'm able to achieve x. And this expansion is what people call the lazy. This is defined in a recursive way, but you can also define it in a dynamical way. So the domain is still the same. I mean, it's the extended domain. And I go from the ith floor to the ith plus 1 floor. And I use the appropriate map, which looks very similar to what we did with the greedy, except the partition, or the partition where we use the different maps is different. But other than that, it is the same idea. Okay. Sorry, the previous picture was the greedy. This is greedy, and the lazy are these maps here. So they sort of, as you can see, you try to use the largest digit as long as you like. In the greedy, we stopped at an earlier stage. For example, in the first line, we stopped at an earlier stage, but for the lazy, we go on as long as we can. And just as in the case of the greedy, that 0, 1 was an attractor, for the lazy, in fact, this interval is an attractor. So once you hit this interval, you will never leave it. So again, the dynamic, although we defined it on a big set, but in fact, the dynamics gets shrunk to the right part of the tower. And also, as in the classical case, it's not hard to see that these two maps, although they generate different expansions, but on the dynamical level, they are really isomorphic. And the isomorphism is as simple as you can think. If you are on the ith floor, then you stay on the ith floor, and the x gets flipped to x beta I minus x. And this map, phi beta, that I defined here, really conjugates the greedy map T beta and the lazy map L beta. And because of that, remember, for the greedy, we have an invariant measure that was my mu beta. And because of this conjugation, we can define a new measure, mu prime beta, which will be invariant for the lazy map. So dynamically, it's a bit silly because it's isomorphic to the greedy. So whatever we say about the greedy will also hold for the lazy. Okay, so they are isomorphic. All right. I know that some of you, I think I have time. Some of you like symbolic dynamics. And as in the classical case, with the greedy expansion, you can, there is a famous beta shift. You can look only at the expansions generated and study the symbolic space. And here we have the same thing. But of course, because at each level we're using different digit sets, which means the base is really, we have to shift the base. My thing is not highlighting. So the base, how we start the base depends on the level we are in. So our shift space d beta n is the collection of all expansions that we get on all, if we visualize X on any of the levels. And of course, we have to close it up. So we close it, and as beta will be a closed shift invariant set. And also Emily and Celia proved in their paper that the shift behaves the way you want it to behave. So if W is in d beta n and you shift it, then the shift of W will be in d beta n plus 1, just because your beta now will start 1 unit later. And you can also look at the symbolic space. You can give it a measure structure, which is just the sigma algebra of the cylinder sets, but on each level you restrict to the appropriate cylinder sets. What I'm trying to say is that on each level we have different digit sets. So that's why we have to restrict to the digits that are given on that level. But to define things in one shot, we're going to look at A beta, which is the maximum digits. So we look at all the digit sets that we get, and we look at their unions. But of course, on the ith level, you're only going to use the digits designated to that level. So we can make a measure structure out of this symbolic space, and we can define the shift in the same way by just moving a sequence on the ith floor to a sequence on the ith plus 1 floor, and and we can define isomorphism between the real space and the symbolic space by mapping a point on the ith floor to a sequence that lives on the ith floor. And these two maps commute, so it's a conjugation. And then you can do the same thing, because we have an invariant measure for the real space, that is for T beta, we can lift it via the isomorph or the conjugation to get an invariant measure for the symbolic space. So everything can be repeated as in the classical case. Of course, there is a little bit of complication because my digits are changing. So these are all formalities that one have to take care of, but the analysis is very similar. Okay, so now let me come to the last part of the talk. All right, so I have my beta, and once again, I'm writing the period, but of course it's an infinite cyclic sequence. So if I take this sequence and I start on the 0th level, on the 0th floor, and I expand using this map, big map, I get expansions the way you are seeing them here. And on purpose, I wrote every P term on one line. So you can see that every time you finish a P terms, then the next, on the next level, if you look at just the last term, so if you just look at the last term, then you are actually having powers of the same beta. So what we're going to do, I'm going to group every P terms together. So the summands on the first line, I will write them as one fraction. The summands on the second line, I write them as another fraction, etc. If I do that, then I get an expansion that looks like here. And you can see that now my denominators look, my denominators look like the classical case. A base, which happens to be a product, is I'm taking the powers of it. So this is really like the classical expansion, but the difference is that my digits are no more integers, but they are in Q beta 1 up to beta P minus 1. So they are, if you like, quadratic rational of in the extended Q of beta 0 up to beta minus 1. I cannot come with this word. So we get a general digit set. Okay, but these have been studied actually by one of my students in her PhD. And this expansion, if I group things together, every P terms together, this is actually the expansion I get if I were to apply the map TP starting from the 0th floor. Yeah, and my digit sets, let me call the digits that I get here, let me collect them in a set. I'm going to call it delta beta. And these are the expressions that I'm seeing in the numerator of these reduced fractions. And this new expansion, I'm going to call it p-blocked greedy expansion. It has the name greedy just because it came from the greedy map. But one essential question is that, is this a greedy expansion? That is, are we, although my digits are not integers, but they are real numbers. So am I picking the largest possible real number at every stage of the expansion? Okay, so let's study this digit set again. This digit set actually is the image of a symbolic set. The map is f beta, and I'm looking at, p blocks of digits. And if I look at f beta, which just, so if I take p digits, the map f beta is defined in this way, and it's exactly done in, it is defined in such a way that I get the numerators of these p blocked greedy expansions. So let me mention here that although the A0, AP minus 1 came from the greedy, which means in the lexicographical ordering, I do start with the largest expansion, but in the symbolic sense, the sequence of digits are larger in the lexicographical ordering. But when I evaluate them, it's not necessarily true that the evaluation will respect the lexicographical ordering. It's possible that I have two sequences, one larger than the other, but when I evaluate, I get the reverse inequality. So here I am actually repeating what I just said. When is the p-block greedy or lazy equal to the greedy or lazy in this space, but with a general digit set? So I will tell you a little bit more about what I mean by a greedy or a lazy with a general digit set. Okay, this greedy or lazy expansion with this particular base and this particular digit set are generated by maps, which I call T, and I put the base here and the digit set here, or an L for the lazy, and they are defined as follows. So what you do, you take your delta beta, which are real numbers. There are only finitely many of them. I order them in the way in the Euclidean order, so the usual order. And so these are evaluations of blocks of digits of length p. And I define the, so in general, when I say I have a greedy map with base beta and digit set delta beta, I'm doing very similar to what I do, sorry, in the classical case. I do beta x minus the appropriate digit, if I am in this interval. And these digits are, in a sense, the largest possible digits that I can use if I am in on these intervals, the di over beta, di plus 1 over beta. And similar for the lazy, but in a, but in a sense, I'm using the smallest digit available to me. So I do this very similar to what we do in the classical case, except my digits are no more integers, but they are real numbers. So this is an example of, on the left, of a greedy map. I have two base with period 2. And on the right side, I see the lazy counterpart. So the greedy all start from the x-axis, and the lazy, they sort of like to take their time, and they start from the axis x beta, or y is x beta, sorry. Okay, so let me summarize again. The p-blocked greedy expansion that you get from the original alternating base greedy expansion is actually coming from the composition of these maps, and it looks like I'm multiplying my base, which is the product of the betas, and then I subtract f of the A's that are available to me, or depending where X lies. And the A's, this sequence of digits, are lexicographically largest element of my symbol space. Sorry, such that if I evaluate and divide by the base, I'm still less than or equal to X. This is actually what we do in the greedy case. So the p-blocked greedy, look, first it starts with the largest lexicographical and then evaluates. And the greedy with this base and this digit set also does something similar. It has the same slope, and it looks like I'm doing the same thing, f of a0 up to ap minus 1, but now f of this is the largest real number in delta beta that satisfies this. So in the greedy, in here, we looked at the largest evaluation that I get, and in the p-blocked, we looked at the largest lexicographical, and then we evaluate, and we might use the largest when we do that. So in fact, at the beginning here, I have some technicalities because my script T beta lives on a different space, lives on these towers, and my greedy maps live on the unit interval. So the delta 0 and the pi 2 are just to formalize things and see things on the line. But in any case, the greedy, in the greedy sense, is always less than the p-blocked greedy, and the lazy is always greater than the p-blocked greedy, greater or equal than the p-blocked lazy. And the question is, when are these the same? This lemma is not relevant here because I'm not doing any proofs, but the point is, if this evaluation function f beta is non-decreasing, then indeed, or if you like increasing, then the p-blocked greedy is the same as greedy, and the p-blocked lazy is the same as lazy. So in a sense, we have an optimal expansion. And it's not hard to see that if your base has period 2, that is, you're only using beta 0 and beta 1, then the p-blocked greedy and the greedy are always the same, and the same thing for the lazy. But the converse is not true if you have more than 2 bases. Okay, so this is an example of period 2 base, and you have equality. So on the left, I see either the p-blocked or the greedy. They are the same, and this is the p-blocked lazy or the lazy. And now I have an example of 3 bases. So I have phi here is the golden mean, and so I have a period 3, and f beta here is not non-decreasing. So the evaluation of 0, 1, 2, which is smaller. So 0, 1, 2 in the lexicographical ordering is less than 1, 0, 0, but the evaluation of 0, 1, 2 gives you a bigger answer than the evaluation of 1, 0, 0. And you see that the 2 maps are not the same. So on the left side, the figure on the left side is the greedy, and the figure on the right side is the blocked greedy. And you see that they are actually the same, except where I see the red lines. The second red line here is different than what I see on the right figure. And you can see that the left figure is smaller or equal than the right figure, because the second red line sends things more to the near the origin, while the p-blocked greedy sends it far away from the origin. So the greedy is more efficient than the p-blocked greedy, or in this case, 3-blocked greedy. And this is the figure for the lazy. And in fact, I could have taken the figures I have here and just rotated them, and I would have gotten the figures you're seeing here. So indeed, here the evaluation is not non-decreasing function, and that's why you don't get equality. But it doesn't mean that every time I get, so what I want to say, it's possible that your evaluation is not non-decreasing and still you get equality. And this is an example of a base with period 3. F beta is not non-decreasing, but just because 0.13 is smaller than 1.00, but the evaluation is bigger, and you see exactly the same. So we don't have necessary and sufficient conditions, so we only go in one direction. And let me end by listing few open questions or things that one can still investigate. We looked at greedy or lazy, but you can look at, there are uncountably many possible algorithms. For example, you can look at algorithms similar to the what we call beta x plus alpha modulo 1 algorithms, and you can see whether you get similar things. I bet you do. You can also look at the random expansions. If you were to overlap the lazy and the greedy towers that we get, you will see that there are regions where you have where the two maps are the same, but there are regions where the two maps differ, and you can sort of use a random algorithm. You can flip a coin every time you have a choice, and you can define a lazy random algorithm, and you can ask the same questions, study the dynamical properties of this new transformation. Now, we also saw that when we look at the p-block greedy, sometimes you get them equal, sometimes you don't. And the question is, you can study how big is this set of bases for which the p-block greedy is optimal, that is, they are the same. We also found a measure mu beta, which is absolutely continuous with respect to Lebesgue measure. One can, this is for the greedy transformation. So one can ask whether it's the measure of maximal entropy. This happens in the classical case. And a very natural question is the last one. We looked at periodic application of our transformation. How about if you don't do that? Can you it will be an infinite tower. Can you study this transformation? Of course, what comes to mind, and this should be, I believe, the approach. Of course, you can approximate any infinite sequence by periodic ones by just chopping it at the nth level and making n larger and larger, and seeing whether the limit of these towers, converge in a sense to the dynamical system you want. But I have not looked at this yet. So these are still questions that can be investigated. I think I'm done here. Thank you very much for listening. And I'm ready for questions if you have any.
Thank you very much. Let's thank our speaker. Let's see if anyone has any questions. Well, I have some questions from Rafa, who is watching on YouTube. And the first question is, what can you say about the topological properties of the big shift? Namely, if it is transitive mixing, if it has a specification or something.
I cannot answer this question, but I think a lot of this has been studied by Celia Cisternino and Emily Charlier. They have a paper in Monas Hefta where they study the symbolic things of these, and they might have another paper sort of continuation. So I would say a lot of this has been studied, but I cannot answer, but I can tell you where to go to find the answer. Yeah.
Thank you very much. There is another one. Suppose that you fix a beta 0 and pick all the possible bases beta 1 where the construction makes sense. Just two maps. Can you say something about the beta 0, beta 1 greedy expansion as beta 1 increases or decreases?
So you fix beta 0 and you let beta 1 vary.
Yeah.
like what kind of questions you are sort of thinking about?
Sorry, that if there is some sort of dependence, once you fix an element of the base, what type of movements or what type of behavior do we have when the other one is moving in just a period of size 2?
Of course, your digit step 2 will change with the change of beta. I don't think dynamically it would make any difference, but in terms of the expansion, I'm not sure what kind of question you would like to know, actually.
Yeah, I think that's right from a dynamical point of view. That it's.
I think from the dynamical point of view, it really doesn't matter what the beta is. Of course, your measures are changing, but you can still find in. Okay, I think I can answer one. Well, I don't know if I can answer one thing, but I can predict what the answer is. Okay, so we have this invariant measure, mu beta, that we have defined, and this is absolutely continuous with respect to Lebesgue measure. And one can, for example, ask whether this invariant measure changes, or the density changes continuously with the change of beta, or so questions like this. I bet the answer should be, it is possible to prove that, for example, if I look at the density of 0, how often does 0 occur? As I fix one base and I let the other vary, I bet that it changes continuously. I think this should be true.
All right, thank you very much. I don't know if there are any other questions.
I guess
just,
not.
I only say to say that it was a fantastic talk, Karma. Nice to meet you.
Yeah, thank you very much. Nice to meet you too. Yeah, I also know your name, and it's nice to see the faces associated with the names.
And you can come here to Cuernavaca when you want. We are trying to make some. I don't know if a workshop or something, some visit if you want to be.
Yeah, that would be lovely. Yeah,